Good day and welcome to Math 111H Calculus 1 Honors, The Joys of X. Today we'll discuss maximum and minimum values of functions. An important area of application for methods of calculus is in the area of optimization, finding the best way to do something. Where does a function reach its maximum value and what is that value? That's an important question, and it's useful in understanding how a business might maximize its profit or how a production company might minimize the amount of material that it uses in order to make its product. It's also useful in minimizing the amount of travel time. Minimization and maximization is very important in the real world, and so first we'll learn about it in the context just of graphing and of functions. First of all, let's define a maximum. A function has an absolute or global maximum at a point c, f of c if f of c is bigger than or the same as any other value of f in the domain. In other words, on a graph, it's higher than any other point, might be equal to some other highest point, but the absolute maximum is the highest that a curve gets. Similarly, a minimum is the lowest that a curve gets. A function has a local or relative maximum at a point c, f of c if f of c is bigger than or the same as any other value of f on an open interval near x equals c. So in the case of a local maximum, what we're saying is this is the highest point that we have nearby. That there might be a higher point further away. So for example, if you spoke about altitude of mountains, so there might be a hill near you. Well, that's the highest altitude that you have near you, but Mount Everest might be the highest on the entire planet in the whole domain. Similar definitions apply to minima, and these maximum and minimum values of f are called extreme values, just another term. So let's consider an example, and let's take a look at the slopes at these extreme values. Let's start on the left. The leftmost point, we have an absolute minimum. No other point on the curve is as low as the curve is at A. Okay? We have a maximum at B, but it's not the highest. At D, we have the highest. That's the absolute maximum. At B, on the other hand, we have a relative maximum. At C, we have a relative minimum. Between B and C, we have another relative minimum, another relative maximum. And here between C and D, we have a point where the curve is flat. It's neither a maximum or a minimum. At D, we have the absolute maximum, but that's also a relative maximum. So local maximums and minimums can be absolute maximums if they are the highest or lowest point on the curve. And at the end, we have neither a maximum or a minimum because at this end point, in order to be a local maximum, one needs to have an open interval around the point. So at E, we have neither a local maximum nor a local minimum. Let's take a look at the slopes at these maximums and minimums. Notice at the top at D, the curve is flat. The slope is 0. At this relative minimum at C, the slope is 0. Also at these other little minimums, the slope is 0, all but the relative maximum at B. And there we have a corner, so the slope does not exist. The slope from one side is not equal to the slope from the other side. And so the slope does not exist. So what we can take with us from this curve is that when we have maximums and minimums, that the slope tends to be 0. Either that happens or the slope does not exist. The derivative would not exist there. Okay? However, if the slope is 0, that doesn't mean that you have to have an absolute maximum or a relative maximum or a relative minimum or an absolute minimum at the point, as we see at this point between C and D where the curve is flat but there's no local maximum or minimum. Let's also discuss the extreme value theorem. And this theorem is too hard to prove for this course, but we'll just state it. If a function is continuous on a closed interval, like the function below, which is the same as the function we showed on the previous slide, then the function must attain its absolute maximum and absolute minimum values on the interval. So this curve is defined on the entire interval from A to E, and therefore it actually must hit its maximum value, which it does at D, and it actually hits its minimum value, which it does at A. So we note that we have a maximum that's in the middle of the interval and a minimum that's at the end of the interval. So if we have a closed interval, then the function will attain its maximum or minimum, and those might occur either inside the interval or at the end of the interval. Let's just take a look at some cases where the extreme value function does not apply. Take a look at the curve y equal x from 0 to 1, but on the open interval from 0 to 1. Here the curve does not actually hit its maximum or minimum. If it were on the closed interval from 0 to 1, yeah, the maximum would be at x equal 1, y would equal 1. At x equals 0, y would equal 0 would be the minimum. But since we don't actually get to x equals 0 and x equal 1, we don't actually attain the maximum or the minimum. Another case is a curve that's not continuous, does not satisfy the conditions required for the extreme value theorem. Function must be continuous. For example, if we take f of x is 1 over x squared from minus 1 to 1, well, we hit the minimum value 1 over 1 and 1 over 1 at both ends. So the minimum value is 1, but the maximum value is not actually attained because the function is not continuous. As a matter of fact, the function does not exist at x equals 0. So the function must exist on a closed interval and must be continuous in order for the conditions of the extreme value theorem to hold, such that the maximum and minimum values are attained, have to be attained on the interval. So some of the results that we get from the ideas that we've presented today are if a function has a local maximum or a local minimum on an interval at a point c comma f of c, and if the derivative exists at x equals c, then the derivative must equal 0. If the derivative exists, the curve is going to be flat, horizontal, be a maximum or a minimum at that point. Let's note that having a derivative that's equal to 0 does not necessarily imply there's a local maximum or minimum at that point. For example, y equals x cubed levels off and then goes on up again. So there is not a maximum or minimum at x equals 0 for y equals x cubed. In the derivative, 3x squared at x equals 0, derivative is equal to 0. So the curve levels off, but there's not a maximum or a minimum. So if you have a maximum or a minimum and the derivative exists, then the derivative is going to be 0. But the other way doesn't work. If the derivative is 0, you might or might not have a maximum or minimum there. You just know that the curve levels off. Maxima or minima can only occur where the derivative is 0 or where the derivative does not exist if the function is continuous. Okay, so we already saw that if the derivative is 0, you might have a maximum or minimum, but we also had a maximum in our earlier curve at a point where the derivative did not exist. So those will be conditions for finding maximums or minimums. You check that the derivative is 0 or the derivative does not exist. Those will be your only candidates for where maximums and minimums can occur. Point C, where the derivative is equal to 0 or the derivative does not exist, those are called critical points or critical numbers. And we're going to find that we'll only need to check on our critical numbers or at our endpoints to find where maximums and minimums can exist. Let's take a moment for math culture. There were two mathematicians who were out fishing on a lake, and they were just having incredible luck. Every time they cast out their lines, a fish would immediately bite, and it wasn't too long before they filled up their buckets and decided they could take no more. So the first mathematician says to the other, "Boy, were we lucky today. I wonder if we'll ever find this spot again." The second mathematician says, "Don't worry, I marked an X on the side of the boat." The first mathematician responds, "You dummy, what if we don't get the same boat?" Thank you for joining us today. Have a great day, and may the power of math be with you.